Welcome back, everyone, or I should say, welcome, cadets, to the Celestial Academy. I am absolutely thrilled to have you here for this orientation. Today, we're embarking on a mission through an explainer that will serve as your ultimate briefing into the STEAM universe. We're going to explore exactly how science, technology, engineering, arts, and mathematics, well, they don't just exist in textbooks. They integrate dynamically to transform ideas into reality, build brilliant solutions, and literally shape the future. If you've ever looked at a massive, complex problem and wondered, man, how do I even begin to solve this? You are in the exact right place. Let's get started. Okay, let's dive into this incredibly fascinating quote right off the bat. Here, scientists clean and builds. Art inspires Fivi mathematics. Now, I know the phrasing from our source is a bit poetic, maybe a little unconventional, but the underlying message is incredibly powerful. It tells us that these disciplines absolutely do not exist in a vacuum. Science isn't just theory, it builds a foundation. Art isn't just decoration, it breathes inspiration into the most complex, heavy mathematics and engineering. In this universe, these fields constantly orbit and empower one another to create true innovation. Here is our exact flight plan for today's explainer. 1. Welcome to the STEAM universe. 2. Decoding technology and design. 3. The Idemic navigation system. 4. Missions in the real world. And finally, 5. Impacting society and environment. We've got a lot of space to cover, so let's keep moving.
Section 2. Decoding technology and design.
You know, often when we hear the word technology, our brains immediately picture glowing screens, smartphones, or advanced AI. But the curriculum gives us a much broader, much more empowering definition. Technology is the use of knowledge, skills, values, and resources to meet people's needs and wants by developing practical solutions to problems, all while taking social and environmental factors into consideration. It is the ultimate human toolkit. It's not just about what you can build, it's about using your values to build something humanity actually needs.
Now, what's really interesting about this slide is how it maps out your literal career flight path. Look at the flow from the bottom up. You start in the GET phase, that's grades 7 to 9, laying down your foundation in basic technology. Then, as you launch into the FET phase in grades 10 to 12, you begin branching out into specialized fields, things like civil technology, electrical technology, or engineering graphics and design. Finally, you reach the top tier, HET, or higher education and training. This is where the skills you're learning right now translate directly into becoming the engineers, architects, technicians, and artisans of tomorrow.
Look at this bold statement right from the source material. No product has ever been manufactured that did not undergo development through design. Honestly, design is the gravitational center of all those careers we just looked at. It's the crucial translation step that turns raw imagination and scientific facts into cutting-edge reality. Whether you're creating a bridge, a new textile, or a life-saving medical device, design is the engine that drives it from a mere concept into a physical product.
Section 3. The IDMEC Navigation System.
So how do we actually do this? Here is our glowing constellation of problem solving, IDMEC. It stands for Investigate, Design, Make, Evaluate, and Communicate. First, you investigate. You dig in to find the context and the true need. Then, you design by sketching ideas and setting specifications. Next, you physically make the prototype, safely using tools and materials. Then you evaluate. Does this actually work? Does it fit the purpose? And finally, you communicate your solution to the world using plans, drawings, and presentations. This cycle is the literal heartbeat of technological innovation. And this brilliantly illustrates how IDMEC actually functions out in the wild. Notice how the arrows in this diagram don't just march in a boring straight line from start to finish. They loop, they orbit. Evaluate is sitting right there in the middle like a black hole pulling everything toward it. You might be in the make phase, realize a flaw during evaluation, and instantly get pulled right back into design or investigate. It's a dynamic, continuous cycle of improvement. Section 4, Missions in the Real World.
To succeed out there in the field, you've got to master 4 core content areas. First up, structures. Learning how to build frameworks that can actually withstand tension and compression. Second, processing. Figuring out how to alter raw materials to make them better, like, say, waterproofing a fabric. Third, mechanical systems, harnessing pneumatics, hydraulics, and gears to create movement and mechanical advantage. And fourth, electrical systems, building safe battery-powered circuits to control your devices. These are your raw ingredients for basically any mission.
Let's move to and see how this builds when we actually combine our navigation system with those core skills.
Here we can see our cyclical IDME process paired directly with the curriculum outline for an actual grade 7 electrical and mechanical mission. It's totally fascinating to see how that abstract concept is used to execute some highly specific real-world technical requirements. Let's look really closely at that specific mission, the electromagnet crane. Here, cadets work in teams to design and build a model crane. But it's not just a stationary model. It uses a crank and pulley system. There's your mechanical knowledge. To carry an electromagnet powered by a battery. Boom, there's your electrical knowledge. And the real-world application? Sorting ferrous metals, like iron, from non-ferrous metals for recycling. You're investigating a real environmental need, designing a mechanical framework, making an electrical circuit, and evaluating its lifting power. It's the whole shebang.
Here is another vital link. Once again, we see the IDMEC process, but this time it's paired with the curriculum for processing materials. This really drives home that the design process isn't just for building rigid moving machines. It is equally crucial when you're chemically or physically altering materials to serve a brand new purpose.
Which brings us to a deeply humanitarian application, the refugee shelter mission. In this scenario, you're using the design process to address an urgent, real-world crisis. Think about it. How do you provide emergency structures for displaced communities? You have to investigate the properties of local materials. You have to figure out how to process textiles to make them waterproof and fire-resistant. The skills you're learning here aren't just for passing a test. They have literal, life-saving applications when deployed in emergency survival situations.
Section 5, Impacting Society and Environment.
You know, a true creator doesn't just build blindly. As the curriculum outlines, you have to keep 3 absolutely crucial considerations at the forefront of your process. First, integrating indigenous technology, looking at how traditional methods have successfully used local materials for generations. Second, counteracting bias in technology, which essentially means making sure your design functions for everyone and doesn't accidentally disadvantage certain users. And third, assessing environmental impacts, asking those hard, practical questions, like whether your new design produces harmful waste. Being technologically literate means taking full responsibility for the entire life cycle of your creations. So the crucial point is the tension between creating solutions and managing consequences. Technology is kind of a double-edged sword, right? It has immensely positive impacts, but it can also cause profound harm. The source material specifically tasks learners with investigating massive issues like acid mine drainage, which is a severe negative byproduct of the mining industry. Your job isn't just to design the mine, it's to design the systems that counteract the environmental damage the mine leaves behind. You literally have to be just as skilled at healing the environment as you are at harnessing it. And that brings us to the end of our orientation explainer today. We've decoded technology, we've mastered the IDMEC navigation system, explored real-world mechanical and humanitarian missions, and faced the heavy responsibility of our environmental impact. The tools are laid out right before you. The scientific foundations are built, the artistic inspiration is ready, and the mathematics are calculated. So I leave you with one final thrilling question. With the entire universe of STEAM at your fingertips, what future are you going to design? Keep learning, keep investigating, and I'll catch you in the next one.